To continue from where we left off yesterday we were talking about Fibonacci and recursion. Yesterday we were talking about recursion, and we want to revisit the Fibonacci sequence. Yesterday we were talking about the Fibonacci sequence. We did do factorial. We drew it out as to what it is and why it's best solved using recursion. But we did not exactly code out what Fibonacci is in code, right? But to revisit what the Fibonacci sequence was, we said Fibonacci formula uses n minus 1, n minus 2, and you add the two values together, right? Everybody recalls the formula, yes? So it said n minus 1 plus n minus 2 gets you that Fibonacci number at some n value, right? So we concluded yesterday by doing some fib of, for example, 4. And we said fib of 4 is, to reiterate, fib of 4 is fib of 3 plus fib of 2. And fib of 3 was fib of 2 and fib of 1, correct? Okay, and this is fib of 2 here. Okay, and at that point, our base case, because every recursive call has a base case. And what's the base case here for our Fibonacci sequence? What's a good base case? 2, right? So a mini says 2. So at 2, we return some value, right? So at 2, base case is 2. So if it's 2, we return 1 like we did yesterday. So at 2, we return 1. At 1, we return 1. At 2, we return 1. And here we start adding them up, correct? So for fib of 3, we say 1 plus 1 is 2, right? For fib of 4,
this color thing is how you lost me yesterday.
oh, the color thing?
I feel myself getting lost already.
You got your partner got you. 1 second. Okay. Why is the base?
The base case is 2 in this specific instance?
In all the instances of Fibonacci sequence, just return 1. When you get to 2, just return 1. That's the base case. For factorial, when you get to 1, you return 1.
So Fibonacci never sees 1, is that what you're saying?
No, it doesn't.
It-
Because you're saying that if the base case is 2, then why do we have a Fibonacci of 1?
Oh, you mean like why does it? It still will call 1, but 1 is not going to call like minus, right? It's not going to call 0 and minus 1. The base case, it will stop calling itself.
At 2.
Yeah.
Okay, because it still needs to know 2 minus 1.
Exactly. So with the colors, Mr. Eric, you don't like the reds, huh?
I'm not gonna lie, but she asked because what you showed me that I don't know what's going on.
Oh.
Okay.
I understand Fibonacci already though, so you don't
Okay.
have to explain it,
But here we're just trying to show how it's done recursively. If I say I want the fib of 4 goes to call fib of 3. It also calls fib of 2. It's not done. Fib of 3 will call fib of 2 and fib of 1. At that point, they'll start returning their values, right? So fib of 2 and 1 will return back to the caller. So what happens here is 1 and 1 is 2. It returns the value up here. Okay? 2 plus 1 is 3. It returns the value back here. And at that point, in your console, you'll have the answer. Very similar to our factorial case that we did, right? So that's what it does. We're just trying to draw out what happens recursively. Cool? Any questions? Okay. So we need a base case for every recursive call we do. And our base here is 2. Let's go to code it out. Hello, play.
So in factorial, the base case is 1 because we're just going to...
The formula states where n is greater than 1,
Right.
right?
Oh, greater than 1, not greater than or equal.
If it's 1, it's just going to return 1 based on the formula. Every formula in math or whatever you have has some case where n equals to some number, you return some number. In that case, or factorial, where n is greater than 1, you return, well, where n is less than 1, you return 1. right, for factorial. So when you get to 1, you just return 1. You don't continue calling that function again, right? That's the base case.
No, I get it.
No, that's fine. Okay, so let's go create Fibonacci here. So we said create a function. You could use the same playgrounds we had yesterday. Or if you didn't have a playground, you could create a playground. Okay, so here we have Fibonacci, and we start off by saying some n value, and we return some integer. Sounds from the computer? Okay, we said we have a base case in every recursive function. What is our base case here? 2. So we'll guard against 2. So we'll say guard where n is greater than 2. Else return, what do we say we're returning? 1. And now we need to go ahead and perform the Fibonacci formula. Fibonacci is n minus 1 plus n minus 2. Yes? So here, what we want to do is return Fibonacci of n minus 1 plus Fibonacci of n minus 2. That's it. It's really just plugging in the formula into the function. Right? That's where recursion becomes very powerful. Right? The thing you say is the thing you write with some base case. My base case, n is greater than 2, keep calling. You get to that number, you return 1. Okay? And Fibonacci n minus 1, this is exactly what we just did. Every instance calls until it gets to that base case. Left and right adds itself up as it returns to the caller. That's why I go to my favorite drawing here, Mr. Eric, and I say if I'm doing fib of 4, fib of 4 calls fib of 3, right? It also calls fib of 2. Fib of 3 calls fib of 2, also calls fib of 1. When they get to the base case, they add the values and they return it to the caller. What is the caller of this particular function here? It's fib of 3, correct? So the value, the result gets returned to fib of 3. Okay? Okay. Oh, let's test it out. What do we have here? Let's test it out with Fibonacci of 4 and play. So as we did in our drawing here, fib of 4 is 3. Right? We get back the result of 3. Comedy out. Okay. Say that again, I'm sorry. I mean, it's 4 return 3, right? So going back here, we have n is equals to 1. We just tested n equals to 4, correct? Guys, we tested n equals to 4. What was the answer? 3. So we could keep going here. 3 and 1 is 5. This is 5. 5 and 3 is 8. This is 6. This is 13. This is 7. And this is 21. This is 8, right? So the question was, let's just do 8, right? So we could test 8. We could go back to our code and we could put in Fibonacci of 8 and run it again, and we get 21. Okay, everybody? When we start going bigger, put 20 in there. Look at, but look at how many times it's running, right? Look at how many times Playgrounds is running. The bigger the number goes, the more times it's running. That thing just gets crazy really quickly. That's where we say we introduce dynamic programming. right? We need to cache the results. And what does, let's go back here. What does dynamic programming do? As we said yesterday, we have things that's repeated. Here we have things that's being repeated. Mr. Eric, I'm going to introduce more colors. We have fib of 2 being repeated here. Fib of 2 repeated here, fib of 2 repeated here. So we want to be able to cache those results. Everybody? So we'll use memorization to cache the results. Let's go ahead and do that. So we'll create an X function. We'll call it dynamic fib. Takes in same sort of arguments here. We have n and we have int, and it returns some value of integer. But a couple of things are starting to be different. We need some sort of way to cache our results. Bless you. We need to be able to cache our results. So we'll cache our results with some dictionary here. I'll call it fib. And it's an int and int. So we have a dictionary where the keys are ints and the values are ints. Now, let's go ahead and see if there's a result. Before we even call Fibonacci, before we even call our function, we want to see if we have that value already. Okay? Do we have the value already? So do we already have the fib value? Okay, so here we'll say if let fib result equal to, we'll use our dictionary and we'll search. We'll say fib dictionary, do we have the value already for n? If we have the value for n, we simply just return that value. Okay? If we do not have the value for n, we continue doing, return result here. If we do not have the value of n, we go through the same base case. We'll say guard, very similar to what we did earlier. We'll have our base case here. Return 1. Okay? If it's greater than 2, we'll go ahead and find the result. So we'll say fib result, go ahead and call fib, dynamic fib, and minus 1 plus dynamic fib and minus 2. And here, we'll store the result in our dictionary. Store the result in our dictionary. Okay? And then return the result. Cool. So let's go ahead and test that function and see if the number of times, let's test to see if the number of times got reduced. Because the whole point of dynamic programming is to reduce the amount of calls you're making, right? We don't want to repeat ourselves, so we cache the results. We cache the results right here. We cache the results right here. Cache the results. Better known as memoization. Okay? Let's go test it out. So dynamic fib of 20. We did it up here, came back 67 times, or 6,700 times, sorry. Let's test our dynamic part of it. Look at that. Would you say that's a benefit? That's a big optimization there? I would say yes, it is. Because I'm not anywhere close to even 20. Here, I'm calling this thing 6,000 times, right? Here, the call is happening 18 times. Okay? Big difference. So if you're submitting some code where you know for sure that it's happening multiple times, use dynamic programming to catch the results of the thing, right? Use a dictionary, store the results, and then continue on with your regular logic, okay? So with the problem we have today, you'll use what we just did today to solve it. Cool? So we'll have the Fibonacci sequence there, where you're keeping count of the first 3, and the value, the current value is the first 3 values. Very similar. So we'll come together and we'll go over that together as pairs for the rest of the day. Any questions with everything? Anything with yes? How are you doing with the first part of it?
Yes.
Okay. The second part of it says, okay, that works, but we see it's being called way too many times. And in the drawing, we see we also doing it multiple times, correct? So how can we make that better? Save the result. So now every time, before we even call the result, we see if the result of n exists, right? This is a dictionary. It saves key value pairs. So if you have a dictionary here, I have a dictionary, and I have, for example, fib of 4, I have 3. You agree? Fib of 4 is 3. So if the dictionary looks it up, it looks for the value for, or it looks to see n is 4. Does the value 3 exist for n? If it does exist, just return that value. Just return 3. Don't go back and recalculate it. This is what the if statement is doing there. Optional binding. Does this value exist? Let's copy this here, and let's put it in here. This is a dictionary. This is a dictionary. Does the value, is there a value for the key n? N is 4. Yulia? If, for example, I say I'm doing fib of 4, for example, like, did I do the value for 4 already? Have I done the fib for 4 already? If I've done it, there's going to be a value 3. I'll just return 3 here. Let dictionary equal to 4, 3. And if let value equal to dictionary for key 4, print the value for 4 exists. Else print does not exist, perform search or something, perform operation. Right? So let's run that. Right? So here, this is the same thing that we're doing, Yulia. This is a dictionary, you agree? Yeah. I'm looking to see if there's a value for this key.
Yeah, because you said this value is like
Yes. But it happens for every single value that's being done. If the operation starts from 4, 4 calls fib 3 and fib 2. Each of those, it searches, do I have a value already for this? Yes, Greg?
So along that exact line, when we call Fibonacci 20, just below that, sorry, dynamic fib 20, dynamic fib 19 through 1 is essentially logged in the dictionary.
Yes, exactly. So I don't have to do that operation again.
And that's why it's not doing it thousands of times. It simply looks it up and says, hey, I did this.
Exactly.
Where if I did dynamic fib 21, it would need to run extra time.
Yep.
To determine that.
Exactly.
And then so.
Exactly. The whole point of it, Yulia, here is to see, save the operation, right? If I've done a job already, I don't want to do the job again.
Yes, I don't understand if when this function do this job.
Well, here it did. Here at that point, the first time it runs, it is 0. There's nothing. Do you agree? Like if I do fib 4, it doesn't exist, right? So it goes in here. It says 4 is greater than 2, right? It doesn't return 1. It goes here. It performs 4. You agree? It performs 4. It has the result here, whatever the result is. It stores it here, right? So when it goes and it calls again, at that point it has the value. Right? Cool? That's dictionary there, that's not recursion. So be careful there. Go back and see and make sure that the whole like searching the dictionary is solid, because a lot of problems has dictionaries in there or frequency dictionaries in there, right? And using them, they're very powerful, knowing that yes, the first time around it doesn't exist. But as I start doing operations, I put values in there. Next time I come, there'll be a value. Or some value. Chelsea?
Is there a limit to the amount of values you can catch? Because I tried, the first time I tried 100 before, it just like.
Ooh, be careful with that.
Yeah.
Fibonacci is very dangerous. Don't put a big number in there.
I stopped it. But
Yeah.
now that we have this, I figured it would run less time.
Maybe comment this one out. This guy. This guy is going to be the bad guy there. I would not test the limits of it too much there on your machine. Just keep it small. I think your problem might be like 25 or something like that, like the problem for today. So 25 is fine. That's still a big number. You see how big that number is? And if you have to do 25 in here, let's see what that does. See that? Be careful there. See that? Be careful. Cool? So let's really be careful with like when we're doing recursion and observe if you have repeated values, catch those repeated values using the dictionary. Right, Julia? Right? And first you check to see if the value exists. If the value exists, use it. If not, go ahead with your regular logic. Right? Because that logic here from 27 to 32 is very similar to what we're doing in our Fibonacci here. But the only difference is the storing and the retrieving. On line 24, we're retrieving. Retrieve. On line 24 here, we are retrieving. And on line, here we cache. Cache is saving. Any other questions before we end here? Any other questions? Okay, but keep in mind that go back, if anything, go back with your partner, go back through exactly what we did, step by step. What's happening on line 1? What's happening on line 2? Write it out, understand what's happening, type it out again. Do it on the whiteboard. Actually, just do it on the whiteboard, because we did it in code already. Do it on the whiteboard and talk about every line you're doing and the why before you actually go to the problem of the day. Is that working for everybody? Cool? All right, so let's stop here.